Assalamu alaikum, dear students. This is video lecture number 2. Before starting the fluid properties, I just want to give you a quick review of the previous lecture, that in which we have studied some basic properties, just like the fluid mechanics. So what is fluid mechanics? The fluid mechanics is the science that deals with the action of force on fluids at rest as well as in motion. In the fluids are at rest, the study of them is called fluid statics. That means if the velocity is 0 and fluid is at rest, so such a study of fluid are called fluid statics. If the fluids are in motion, when pressure force are not considered, the study of them is called fluid kinematics. If the fluids are in motion and the pressure force are considered, the study of them is called the fluid dynamics. Now let's move on to the fluid properties. So fluid properties are very important to understand. Without understanding of the fluid properties, it would be very difficult to understand the behavior of fluid mechanics, and it will also be difficult to derive the new empirical relationship without using the fluid properties. So let's begin. The fluid in the first one is the fluid density. The fluid density or the mass density is indicated with the Greek letters mu. So what it says, the density of fluid is defined as the mass of the fluid per unit volume. Okay, so that means the amount of matter or amount of substance in a given volume. So mathematically it is defined as the ratio of the mass to the volume of the fluid. So mu is equals to mass over volume. So it is indicated with the density is indicated with mu, mass is indicated with m, volume is indicated with v. Okay, so in SI system the unit is kilogram per meter cube. In English system the unit is pound mass per feet cube. In CGS system is gram per centimeter cube. It is also known as gram per cc, cubic centimeter. It depends, mass density is basically depends on mass and size of the atoms of the fluid. Okay, the fluid have same volume and different mass have different density. It means the molecules of every substance have certain mass. That is, more the number of molecules, more will be the fluid density, as it is mentioned in the sketch in A, in B and C. It has the same volume, but the number of molecules are different. More the number of molecules, the density is higher. Moderate number of molecules, as it is water, the density is moderate, and the wood is a less number of molecules, the density is less. So more the number of molecules, more will be the fluid density. It can also be known as the heaviness of the fluid. So it basically indicating the heaviness of fluid. So some standard value of fluids, the density of fluid 100,000 kilogram per meter cube at the rate of 4 degrees centigrade. Density of mercury is given, and density of air is 1.2 kilogram per meter cube in SI system. If the density is constant, most liquid, okay, the flow is incompressible. So normally the liquids are considered as incompressible fluid, because when we apply pressure or temperature, it doesn't expand much. Okay, the density doesn't change much, it doesn't expand or it doesn't compress in a reasonable consideration. So that's why we consider most of the liquids are incompressible. So if the density varies significantly, that is some gas flow, the fluid is compressible. So gases are normally compressible. So that means the density is a function of temperature and pressure. So consider here we have a two container A and B. So here we have a liquid vapor barrier. This is the liquid vapor barrier. So if we apply a pressure P over it, okay, till the vapor is here, when it will reach to the vapor liquid barrier, after that it will compress negligibly. So in this case we can say that the liquid doesn't change its density. But if we apply the pressure P here, so what will happen? It will compress. Okay. So in this case we can say that the gases are compressible fluid and the liquids are incompressible fluid in general. In some cases, although the gases are easy to compress, then flow may be treated as incompressible if there are no large fluctuation. If the fluid is flowing in a pipe or in a system, if there is no reasonable fluctuation or change in pressure, so in that case we can consider the gas as a incompressible fluid for that particular system or for that particular flow. Since the liquids are incompressible but the gas are compressible and the density of the gas is depending on the temperature and pressure. So how we can find out the temperature and pressure, how we can find out the density of the gas if the temperature and pressure are changing? So we can only find out by using the ideal gas law. So what it says, the gases are highly compressible than liquids. So we need a way to find out the density of the gases with a change in temperature. So change in gas density is directly related to the change in pressure and temperature through equation of ideal. So PV is equals to rho RT. So where P is the absolute pressure and T is absolute temperature and R is the gas constant. Okay. So you must remember whenever you use the pressure and temperature, the unit must be absolute. Okay. Either it is Kelvin or Rankine. And this R is basically the gas constant. The gas constant is different for each gases, and there is another R, that is RU, that is universal gas constant, that is same for all the gases. Keep in mind. So ideal gas equation is also known as equation of states. So what is equation of states? Any equation that relates the pressure and temperature and density of a substance is known as equation of state. So ideal gas equation of state, the simplest and best known equation of state for a substance in the gas phase is PV is equals to RT or PV is equals to rho T, because this is the specific volume. So if you take it, 1 over V is going to be rho. So this is the gas constant and this is the universal gas constant, and here is the molar mass of the gas. Okay, so in this way you can find out the value of the R of the gas. So PV is equals to MRT and PV is equals to NRT. These are the equations that you can use. So the thermodynamic temperature scale in SI is Kelvin scale, and in English system it is Rankine scale. So whenever you are whenever you want to use these equations, so you have to use either Kelvin or Rankine. An ideal gas is a hypothetical substance that obeys the relation PV is equals to RT. Okay, we all know this equation is only applicable for the ideal gases. So what is the ideal gases or ideal fluid? So what is the difference between the ideal and real fluid? So basically the ideal fluids are incompressible, inviscid fluids. Incompressible means density remain constant, density doesn't change. Inviscid means no internal resistance to flow. There is no resistance, okay, so you don't okay. So real fluids are compressible and viscous, yani both things will be need to be considered. Okay, so here is the difference between the real fluid and ideal fluid. So this equation is applicable for the ideal fluid. The ideal gas relation closely approximate by the PVT behavior of real gases at low densities. Okay, in the previous semester we studied the thermodynamics, where we learn about PVT diagram and the behavior of the real gases. Okay, because the real gases behave like an ideal gas at low densities. Okay, that we observed in PVT diagram. At low pressure and high temperature, the density of gas decreases and the gas behave like an ideal gas. Okay, so what's important, at low pressure and high temperature the gases behave like a ideal gas. Even most of the real gases like the oxygen, hydrogen, nitrogen, helium, argon, neon, krypton, even heavier gases such as carbon dioxide can be treated as ideal gas with negligible error. Okay, dense gases such as water vapor in steam power plants, refrigerant vapor in refrigerators, however, should not be treated as an ideal gas, since they usually exist at a state near the saturation. Okay, at low temperature, at low pressure and high temperature, they do not fall in the superheated region. They fall very close to the saturation region. That means there is a water vapor available, so we cannot treat these vapors as a ideal fluid. Now next is the specific volume. So mathematically the specific volume is the total volume of a fluid divided by mass or per unit mass. So V over M, so if we simplify it, we end up with 1 over rho. So it is the reciprocal of the density. The SI unit of the specific volume is meter cube per kilogram in English. In English unit, feet cube per pound mass. Okay. Now the weight density, it is defined as the weight of fluid per unit volume. You need to divide the weight with the volume, so you can get the weight density. So what is the importance of the weight density? It is the force exerted on the given volume of fluid due to gravity. So mathematically it is indicated with the Greek symbol gamma. Okay, the weight over volume. Okay, Okay, we simplified this mass over volume, it become rho is the density, so gamma is equals to rho g. So gamma is the function of temperature. Gamma is the function of temperature, and the value of gamma water is 9.79 kilogram per meter cube at 20 degrees centigrade. Okay, we especially mention here at the rate of 20 degrees centigrade because gamma is the function of temperature. As the temperature change, the value will change. The SI unit of the weight density is Newton per meter cube. In English unit, pound force over feet cube. So density is also density is absolute quantity with respect to location, whereas specific weight or weight density is a variable quantity with respect to location. It is due to the force of gravity. So because if you are moving from earth to moon, the specific gravity will change, but the density will remain same. Now next we are moving on to so here is one example. It is given very simple example. The volume is given 12 meter cube, mass is given 3 kilograms, so we can calculate the density, okay, mass over volume, and we can take the reciprocal of density to find out the specific volume. So now move on to the next slide, the specific gravity. This is a very important parameter to understand. Specific gravity or relative density. The specific gravity is the ratio of weight or mass density to the specific weight or mass density of the standard fluid. So if you know the weight density or the specific weight of a substance, of a fluid, so you can easily find out the specific gravity. So in the fluid we have two entities, it is liquid and gas. For the liquid, the specific gravity is equals to density of liquid divided by the density of water at 4 degrees centigrade. So here we are considering the standard fluid is water for the liquid, and water density is 1000 kilogram per meter cube at 4 degrees centigrade. Okay, this is the at standard temperature. For the gases, specific gravity is the density of gas divided by the density of air at STP. So at STP, the density of air we are considering 1.21 kilogram per meter cube at the rate of STP. Okay. So if you know the density of a gas, so you can easily find out the specific gravity of the gas. If you know the density of liquid, so you can easily find out the specific gravity of the liquid. So what does it indicate? Okay, it indicates or it shows the substance is how much heavy compared to water. Okay, whatever is the substance, it shows how much, it shows the substance how much heavy compared to water or compared to air at STP. So what does it mean? The specific gravity of water at the standard temperature is 1. If the specific gravity is less than 1, the fluid is considered lighter than the water, and if the specific gravity is greater than 1, the fluid is heavier than water. If the specific gravity is less than 1, it means the fluid is light and can flow over the water in a mixture. and if the specific gravity is greater than 1, it means the fluid is heavy compared to water, and if that fluid mix with the water, the fluid remain downside of the mixture. So this is basically the understanding of the specific gravity. Here are in the table the specific gravity of some fluids are given, okay, at 20 degrees centigrade and at 1 atmosphere. It is mentioned. So move on to the example. Normally in the problem, if the specific gravity is given and to solve a problem you need a density of fluid, if it is not given in the problem, so you can find out the density by using this technique. And sometime the specific gravity is given but the density is not given, so by using this technique you can find out the density and you can find out the specific gravity. Okay, so here you see find out the specific gravity of Mercury. So here weight density is given. Okay, here the weight density is given. So weight density of Mercury is 133 and the weight density of the water at 20 degrees centigrade, we know that it is 997. It is 9.97. So 9.97. So if you divide with this, so you will end up with 13.6. So if you want to find out the density, so you can use the same formula. The specific gravity is given, the density of water is given. If you multiply them together, so you will end up with the density of the Mercury. Now move on to the problem. So there is an example 2.1. So what we have to do, determine the density, specific gravity and mass of the air in a room whose dimensions are 4 meter by 4 meter by 6 meter at 1000 kilopascal and 25 degrees centigrade. Okay, as mentioned in the sketch. So 1000 kilopascal is basically the 1 bar, or it is the atmospheric pressure. Okay, so what we have to do, we have to find out the density, specific gravity and mass, and what other things are known. The room volume is given, okay, and the pressure is given and the temperature is given. Okay, so that means we are talking about the air, and temperature and pressure is known, the volume is known, so we can find out the value of density very easily. For the gases, we are making some assumptions, and we are considering the air is a ideal gas. If the air is an ideal gas, so we can apply the equation P is equals to rho R2B. So rho is equals to P over RT, pressure is given 100 kilopascal, 0.287 kilopascal cube is the value of R for the air. Okay, you must keep in mind the whatever the unit of R you are using, same unit you will put it here. If you are taking kilopascal unit, so use unit here kilopascal. If you are using bar here, use bar here. If you are using only pascal, not kilopascal, then this 100 supposed to be 100,000, so it should be in pascal, and this temperature must be converted into absolute temperature scale, that is Kelvin. If you are using Kelvin, use Kelvin. Okay, so in this case, when you end up with, so you will get the density of the air, okay, at this temperature and pressure. Then specific gravity of the air becomes, so you know the density, the specific gravity is the density then the specific gravity of the air becomes specific gravity is the rho over rho H2O. So this will become 0.0017117. So that means it is far above water. Okay. Finally, the volume and the mass of the air in the room. So what we have to do, we have to find out the mass. To find out the mass, we know the density, and if we know the mass, we can easily calculate the, if we know the volume, we can easily find out the mass. So volume we can calculate by using this, because we know that the gas, whatever is the shape of the containers, the gas occupy the whole space. So that means the gases are everywhere. So the volume of the gas is 4 into 5 into 6 is equals to 120 cubic meter. Okay. So mass is equals to rho into V. So we multiply the density and V. So we end up with 140 kilogram. Note that we converted the temperature to absolute unit K from relative unit degree centigrade before using the ideal gas relationship. So you must keep in mind. Next, there is another problem to find out the okay, if 1 cup of cream having a density of 1005 kilogram per meter cube, the cream has a density is given, is turned into 3 cup of whipped cream. Okay, to determine the specific gravity and specific weight of the whipped cream. Okay, so 1 cup of cream is turned into a 3 cup of cream, and we have to find out the specific gravity, specific weight of the whipped cream. Okay, determine the specific gravity and specific weight of the whipped cream. So first of all, we see the matter never change. Okay, the matter never vanish. So the mass of the cream is equals to mass of the whipped cream, because the mass is remain same. Mass is not changing. The volume is changing, but the mass is remain same. So mass of the cream is equals to mass of whipped cream. Okay, so mass of the cream is equal to, if we mass is equals to we can make a relationship between mass and volume. Okay, so mass is equals to rho V. Okay, mass is equals to rho V. So here the density of the whipped cream, mass over volume. Okay, and the density of the whipped cream is equals to mass of the whipped cream divided by volume of the whipped cream. So density of whipped cream is equals to the mass of the whipped cream. How it is going to be? 1500 kilogram per meter cube into V cup. Okay, it is mentioned here, and the volume of whipped cream. Okay, okay, so it's fine. Now if you saw, this is 1 cup equals to 3 cups. The volume is remains the volume of the cup is same. This is the volume of the cup is same. So this is 1 cup and this is 3 cups, but the volume of the cup is same. So here volume and volume can be cancelled. This is going to remain 3. If you divide 105 of 3, it will be equal to 335 kilogram per meter cube. So now you know the density of the whipped cream. So once you know the density of a fluid, you can easily find out the specific gravity, because you know the standard specific gravity, you know the standard density of water. So you divide with the standard density of water, that is 1000, you will end up with 0.335 specific gravity. Now you have to find out the specific weight. What is the specific weight? Specific weight is equals to density into gravity. So you multiplied with the value of 9.81 meter per second square. So the value you end up with 3290. Okay. Next is continuum. So here since we are studying the fluid mechanics, in this case we are considering a continuum approach. So what is basically the continuum? Matter, we all know the matter is made up of atoms that are widely spaced in the gas phase. Okay, yet it is very convenient to disregard the atomic nature of a substance and view it as a continuous homogeneous matter with no holes, that is a continuum. Okay, because we know there is a space, but even then we can consider it is a one unit. That means there is no gap between the atom of the substance. So by using this assumption that all the substance are homogeneous, continuous, okay, as a continuum, the continuum idealized allow us, okay, what is the benefit of it? To treat properties as a point function and to assume the properties vary continuously in space with no jump discontinuities. So because of that, okay, the properties we are measuring at one side, that means everywhere the property is same. So it is not disturbing because of the void area. So this is the benefit of considering it as a continuum. So this is the case in practically all problems. In this text we will limit our consideration to substance that can be modeled as a continuum. So move on to the next slide. Viscosity. This is a very important property of the fluid. You have to understand very clearly because this will be utilized throughout this course, because the viscous flow is depending on this property and the boundary layer theory is also depending on this this property. So you have to understand properly. So what is this viscosity? A property that represents the internal resistance of a fluid to motion or the fluidity. So that means it is a kind of a resistance offered to the force. So what is the drag force? The drag force, the force a flowing fluid exerts on a body in the flow direction. The magnitude of this force depends in part on viscosity. So in the drag force, okay, the magnitude of this force depend in part. So partly depend on the resistance of the fluid and partly depend on the velocity or the energy of the fluid which is present. The viscosity of a fluid is a measure of resistance to deformation. Viscosity is due to the internal frictional force that develops between different layers of fluid as they are forced to move relative to each other. Okay, so this is a very important consideration. The viscosity of a fluid is a measure of its resistance to deformation. Viscosity is due to the internal frictional force that develops between different layers of fluid as they are forced to move relative to each other. Okay, now we will see how we can explain this phenomena, how we can explain the viscosity is. So what is the viscosity? We just read it. The viscosity is defined as the internal resistance offered by one layer of the fluid to the adjacent layer. Okay, so this is basically the relative motion between the two fluids. So what is the reason of viscosity? The reason of viscosity is cohesive force or molecular momentum transfer. So since we are talking about the viscosity of two entities, one is liquid and other is gas. So what is the reason of viscosity in liquid? The reason of viscosity in liquid is cohesive forces. And if the cohesive force, what is the cohesive force? The cohesive force is a molecular. So the cohesive forces are the intermolecular force between the same fluid. It is the force between the two molecules of the same fluid. And the cohesive forces are the forces between the molecules of different fluids. Here in the picture I have showing here the cohesive forces in liquid molecules is much greater than cohesive forces in gases, because we know that in the liquid the molecules are very close to each other and they have a good bonding, but in the cohesive force in the gases we know the molecules are far from each other and they have no attraction between the two gas molecules, is almost negligible. So it means in the liquid basically the viscosity is the reason due to cohesive forces. In gases the viscosity is happening due to the intermolecular momentum transfer. So the molecular momentum transfer in gases is much greater than molecular momentum transfer in liquid, because in the gases we know that what is the molecular momentum transfer, because we know that the gas molecules, each gas molecules have some mass and they are moving with a velocity, that means they have energy in it. Okay, so when one molecule of gas when strike with others or collide with others, so they transfer energy with each other. So they are moving randomly, that means they are colliding with each other more freely in the gases compared to in liquid, because in the liquid they are not free to collide with each other. Okay, they are bound with the cohesive forces. So because of that, because they are hitting with each other very rapidly, because of that they are creating a resistance. Okay, because of that resistance is creating viscosity in gases. So in gases the molecular momentum is the reason of viscosity. If the viscosity is less, the flow will be easy. So now we see how, now let's see how the resistance between two layers occurs. So consider a fluid particle made of different fluid layers moving with a certain velocity. So here are, you can see there is a solid surface, okay, there is a 0, and there is a first layer of fluid, that is 1, the second layer of fluid, the third layer of fluid, and the fourth layer of fluid, and fifth layer of fluids. Okay, so we see how the viscosity appears in the liquid and what is the reason. Okay, so this is a vertical distance or depth of the fluid or the thickness of the fluid. So here the fluid is moving, because fluid is moving we are considering that there is a shear stress is applying on it and it's on the top surface is moving. Okay, the bottom surface is fixed. Okay, since the bottom surface is fixed and very first layer of the fluid is stick with the solid surface due to the cohesive forces. Okay, so that means here the velocity is 0. There is no velocity at the bottom. So here is the 0 velocity. So we are considering u is equals to 0. So from here, as we move up, okay, as we move up, the cohesive forces decreases, but still there is a the adhesive forces decreases, but still there is a cohesive forces between the molecules. So as we are moving up, the adhesive forces are decreasing. So because of that, we got a velocity variation. So we got a curve like this, how the velocity is varying as it is moving away from the fixed surface. When it reaches to its top, the topmost layer has the maximum velocity and the bottommost layer has the 0 velocity, and it is joining with the curve. So here you see, as we are moving up, the velocity is started increasing. The upper layer is increasing further, it is increasing further, it is increasing further. That means U5 is free to move, but the bottom layer is not free. So that's why U5 is greater than U4. The velocity at layer 4 is greater than layer 3. We can see that the here to here is U2 and here to here is U3. So here to here is U2 plus du. That means U3 is equals to U2 plus du. That means there is a small difference which is du. So this movement, that means movement of topmost layer 5 will provide some resistance to bottom layer. Layer number 4 will provide some resistance to layer number 3, and so on. In this way we can say that this movement of one layer provided resistance to the movement of other layer is termed as viscosity. Okay, so viscosity has a effect, the temperature has effect on viscosity. Okay, in liquid, if you increase the temperature, the velocity will decrease, the viscosity will decrease, and in gases, if you increase the temperature, the viscosity will increase. We will see in the later part. But here we are saying because there is a relative velocity between the two layers of the fluid layer, and they are trying to stop each other. Because of that, there is a phenomena which is termed as viscosity. Now move on to the next slide. There is a Newton's law of viscosity. So what is the Newton's law of viscosity? That is also a very important law. It states that all those fluids are said to be a Newtonian fluid in which shear stress is directly proportional to the rate of shear strain. Okay, so what is the shear stress and what is the rate of shear strain? Shear stress, we know that the tangential force acting on a surface of a fluid is called shear stress, and the deformation produced due to this shear stress is called shear strain. But what is rate of shear strain? Let's see here. Consider a fluid element. Okay, in the fluid element we are applying a very small force, that is dF, because on the top surface of the fluid, and because of this small force there is a small shear stress. Okay, that is applying on the top of the surface. Okay, now consider we are talking about the fluid. Okay, so once we apply this force and because of the small shear stress is acting on it, the fluid start deformation. Because we already know how small is the force, their fluid will start deforming, and it deforms continuously. So here we are considering one small particle. The particle 1 at very small time t here, because when we apply a force, it deforms, but it's not stopping. This point 1 then move to point 2, then move to point 3, then move to point 4, then move to point 5. It is deforming continuously. So, but it is quite different than the solid that we have experienced before. So what exactly happens in solid? If this is a solid cube, we are acting a force F, which is equal to a shear force per unit area. There is a small shear force we applied, and because of this there is a small deformation theta occurs. Okay, so this is the deformed shape, so small theta is occur. So for a finite element of a force, there is a finite deformation. Okay, so if you want to deform further, you have to increase the force. Okay, so in this way we can easily find out the deformation by using the relationship, which is shear stress is directly proportional to shear strain, because the strain is fixed for a particular amount of force. That is, due to Hooke's law, we can easily find out the strain. But in the fluid, we applied a force, but the deformation, the strain is not fixed, it's continuously moving. So we don't know the strain, but we can find out the rate of strain, at what rate the fluid is deforming. So here the Newtons give a concept that we cannot find out the strain, but we can find out the rate of strain. So he give a concept which is called the shear stress is directly proportional to rate of shear strain in the fluid. So in the fluid we cannot use shear stress is directly proportional to shear strain, but we instead of that we are using another concept which is called shear stress is directly proportional to rate of shear strain. So tau is equals to this gamma dot is called rate of shear strain. Now let's see how we can find the rate of shear strain in in fluid. Shear strain is not constant, it is moving continuously. Okay, now let's move on. So here in the fluids, find rate of shear strain. How we can find out the shear strain? If we can find the shear strain, so we can find out the force, we can find out the shear stress also. So consider we have a fluid element. Okay, on the there is a two plates. There is a bottom plate which is fixed, and there is a movable plate where we applied the force. So we are applying a force. This is basically a very small element we are considering. The depth of the fluid is dy. Okay, there is a two plates. We are considering there are two plates. Okay, in the between the two plates we have a fluid. Okay, the fluid thickness is dy. Okay, the bottom edge is fixed, that is u is equals to 0. The very first layer of the fluid is 0. Okay, and then it's, as we have seen in the previous slide, the velocity is slightly increasing, and the topmost layer has the maximum velocity, which is equal to, at point A the particle has a velocity du. Okay, this is the, we are considering the maximum velocity, and we applied a small force, that is F, and because of that the fluid started moving. Okay, so that is it is moving with the velocity du. Okay, so we are talking about, so because you see, when we applied the force, the fluid moving continuously. Okay, that means every second, every small time interval, it's changing. So we are talking about a very small time interval dt. Okay, so in dt time, okay, in dt time with the velocity, okay, the particle A move from A to B. So when it moves from A to B, so in time dt, how much distance it will travel? So we know that S is equals to Vt. So this is our velocity and this is our time dt. So if you multiply them together, so you would know how much distance you have traveled from A to B. Okay, so distance traveled AB is equals to du by dt. So now d gamma is basically the strain, is the change in strain. This is a very small strain, the d gamma we have considered. Okay, so now let's consider tangent gamma is equals to AB over AO. Okay, AB over AO. Okay, so AB over AO, so tan theta is equals to this. Since this is very small, so tan theta d gamma is equals to d gamma. So d gamma is equals to du by dt over dy. So d gamma over, so dt will come here, so d gamma is equals to dt and du by dy. So this is du, this is du and this is dy. So this d gamma over dt is equals to gamma dot, which is basically the rate of shear strain. This is also the rate of shear strain, and this is du by dy is the change in velocity with respect to distance. It is also known as velocity gradient or velocity profile. So that means the rate of shear strain is equal to velocity gradient or velocity profile. This is a very important relationship that we found with the small example. So we can write down the shear stress is directly proportional to rate of shear strain. Okay, so since it is very difficult to find out the rate of shear strain, because every small unit of time it is changing, so how we can find it? So it is difficult, so we are replacing this. We can also write down, because the rate of shear strain is directly is equal to the velocity gradient, so we can write down tau is equals to du by dy. Okay, so when we remove the proportionality sign, so we end up with the constant, that is mu, which is dynamic viscosity. So this is the Newton's law of viscosity. Tau is equals to mu du by dy. So this is the Newton's law of viscosity, and mu is the dynamic viscosity. So here the Newtonian fluids, the fluids, Newton fluids are those fluids which follows the Newton's law of viscosity. Okay, so shear stress is equal to tau mu du by dy. The unit of shear stress is Newton per meter square. And then shear force, we can also calculate the shear force. Shear force is equals to, this is the area where the force is acting. Okay, so the topmost layer, so this is the area. So if we multiply it by the shear stress with this top area, so we will end up with the shear force. Okay, so this will be equal to in Newton. So in the above equation, du by dy is the velocity profile, or velocity gradient is equal to the rate of shear strain. Okay, so mu is the constant of proportionality known as the absolute viscosity, dynamic viscosity, or simply viscosity. Okay, so it is indicated with the mu. The unit in SI system is kilogram per meter into second, or Newton second per meter square, Pascal second. Okay, because Newton per meter square is the Pascal into second, or 1 poise, it is also the unit is 1 poise is equals to 0.1 Pascal second. So these are the units, SI units of the dynamic viscosity. The value of mu depends on the fluid, and for any particular fluid the value of mu depends on the temperature. Okay, for any particular fluid the value of mu depends upon the temperature. So here we can see that as the temperature is increasing, okay, the density of the fluid, the liquids, are decreasing with the increasing in temperature, because the arrow is indicating that the temperatures are increasing. So as the temperature is increasing, the density of the liquids are decreasing, but as the temperature is increasing, the density of the gases are increasing. Okay, because the movement, the motion of the molecule is going to be more. Because of that, they are hitting with each other. It's more rapidly, it's faster than before, because in the gases the intermolecular forces are negligible, and the gas molecules at high temperature move randomly at higher velocities. This results in more molecular collision per unit volume, per unit time, and therefore in greater in resistance to flow. Okay. So here you mention the dynamic viscosity of some fluids are mentioned. Here you see the top area, because the density of fluids are the viscosity of the fluids are more comparing to the gases, because the gases have, this is the range of the viscosity, and the fluids have, this is the range of the viscosity. Okay, so here as the temperature is increasing, you see the gases, the viscosity of the gases are slightly increasing. Okay, but here the fluids, as the temperature is increasing, all the viscosity of the liquids are decreasing. So now the kinematic viscosity is equals to, it is indicating with the nu, it is another type of viscosity, that is mu over rho. Okay, the kinematic viscosity, its unit is meter square per second, or stokes. So 1 stoke is equals to 1 centimeter square per second. Okay, for liquid, both the dynamic and kinematic viscosity are practically independent of pressure, and any small variation with pressure is usually disregarded except at extremely high pressure. We call this viscosity as a kinematic viscosity because in this viscosity we do not have any force component. So that's why it is also the reason to call it as a kinematic viscosity. Okay. But for the gases, this is also the case for the dynamic viscosity at low to moderate pressure. Okay, but not for the kinematic viscosity, since the density of the gases is proportional to its pressure. Okay, the kinematic viscosity of gases at high pressure, it varies. Okay, it changes. Okay, that means the kinematic viscosity is the function of pressure. Here you see, here there is an example. The air at 20 degrees centigrade and 1 atmospheric pressure, the dynamic viscosity is not changing, and air at 20 degrees centigrade and 4 atmospheric pressure. So dynamic viscosity is not changing with the change in pressure, because it doesn't vary with the pressure. Okay, it doesn't affect with the pressure, doesn't affect it. But the air is here, because we have a density, here we have a component of density. In the dynamic viscosity we do not have any component of density or others, okay, which depends on the pressure. But here density depending on pressure, because of that the viscosity, the kinematic viscosity is changing.